All right, so 3.2 subspaces sort of piggybacks off from 3.1. A subspace is just another vector space that sits inside of another vector space. Excuse me. So you have to know what a vector space is first, and then if we specify some subcollection, the question is whether or not it is itself also a vector space. And if it is, then it's a subspace. So, some examples from the text. So F, the vector space of all smooth functions. So remember, a vector space has 8 properties. And maybe even more than that, depending. But we start off by assuming the collection is closed under addition and scalar multiplication. So the space of the collection of all smooth functions is a vector space. Smooth means infinitely differentiable. If you add two infinitely differentiable functions together, it's still infinitely differentiable. If you multiply an infinitely differentiable function by a scalar, it's still infinitely differentiable. Any smooth function has an additive inverse. It's just the negative of that, right? There's a zero function. 0 is an infinitely differentiable function. So F is a vector space. So there are lots and lots of subspaces of F. F is actually infinite dimensional vector space, and super useful in a crazy way. So P is a subcollection. Consider all the polynomials. We mentioned this in the previous video. So any polynomial, any degree, any coefficients. That's also a vector space. If you add any 2 of those, you get another one. If you multiply one of them by a number, it's still a polynomial. Any polynomial has an additive inverse, multiplied by -1. 0 is a polynomial, so the 0 element's there. So P is a vector space, and because it's a subcollection of F, is also a subspace of F. Now within P, there's another collection. Consider all the polynomials of degree less than 3. So these are the quadratics again. Well, as we mentioned in the last video, quadratics are certainly a form of vector space. And so they're a subcollection of P and a vector space. So they're a subspace of P. They are also a subcollection of F. So they're a subspace of F. Now, geometrically, you can think of a subspace as, think of the plane, the xy plane. That's a 2D vector space. And so any line forms a one-dimensional subspace. Any line through the origin, because we need to have the 0 element. So the x-axis is a one-dimensional subspace. The y-axis is a one-dimensional subspace. The line y equals x is a one-dimensional subspace. Any vector that lies in that line is a one-dimensional subspace. So it's just a vector space inside of another, and it'll have a lower dimensionality as well. Okay.